Okay, to finish with Meixner condition, yeah, it's a bit like tricky, but we ask for physical thing. We just ask for energy to be finite, and then we need some mathematical formulation. Which okay, makes sense, but it, yeah, we kinda to check it, to have a good, nice condition, we need to solve the problem in the vicinity of the edge, have some series, and then we have like a more useful condition. And that's why the thing also related to something which is called Meixner series. So what we do, we consider only the vicinity. Of course, for half plane, it will work everywhere. But if we consider, for example, like a strip, we can build a solution as a series only here. And I will write down the series. And probably for you, it should be more or less clear how to obtain the series using approaches from lecture 1. Let's see. Of course, the series is some combination of basic functions. So to obtain the series, we just separate the variables. We will have some basic equation for R, and we will have some simple equation which will give a trigonometric solution for phi. You can try to do it yourself. But when we apply Meixner condition to the series, it's quite easy to apply. We just say that all Bn is 0. So Meixner condition allows these terms and prohibits these terms. And finally, like we did this formal mathematical formulation, but also if we want to make sense to people, somebody needs to prove like a limit. Sorry about this. Like this. So we have kind of a very thin, smooth obstacle, and then we consider a limit as this obstacle becomes thinner and thinner and thinner, and we should prove that in this limit we get the same solution as we get from Meixner condition. Of course, I won't be doing it because it can be quite tricky, and we will need to go into functional analysis, which I don't want to do. But you just should be aware of general idea. Okay, and that's it. Once we do all this stuff, we have what is called a well-posed diffraction problem with a unique solution. But before we will start to solve such problems, we need to study some other tools. We need to get hand on the tools to solve this problem. And the most important tool is called second Green's identity. I have a feeling that in Britain it has a different name, but that's how I was taught to call it. So what is this identity? We consider a pair of equations with some right hand side. With the same wave number. And we ask them to be satisfied in some domain. So we have some finite domain omega. We define the inner normal, and we study the following combination. I will there is no difference whether I consider a 3-dimensional problem or 2-dimensional problem. So I will write it as a 3-dimensional problem, but that doesn't change anything. So we consider the following combination. Then I substitute instead of f and g left hand side. So naturally, I get just from substitution. Nothing happened, just this term died because of the cancellation. And then I will try to extract a divergence term from this. So I want to apply Gauss theorem, of course. That's what we always want to do. Integrate by parts, it's that's the only tool we use in analysis. And this is just a fancy way to integrate by parts. Okay, let's extract divergence. We are lucky, and this term dies. So we only have a full divergence term to integrate. The final step. We apply Gauss, or if you go to Russia, this theorem will be called Gauss-Ostrogradsky. And so we have a boundary integral, a surface or integral of the following thing. And second Green's identity is this thing is equal to this. This is probably the most important tool you can find in diffraction theory. Let's study some applications. So let's put somewhere a 0 point, an origin, and put a point source into our final domain and characterize it by vector rs. And consider, let u be just a solution of this diffraction problem, and g be a delta function. And this thing just be a free field Green's function basically. So this field satisfies, I don't know which conditions I take. Yeah, it doesn't matter. Okay, this is, this thing just satisfies Gilbert's equation inside, and this is a free Green's function. So what we get? We substitute, so this part is 0, and this part gives us u, because we integrate with delta function, get rid of the integral, and we will get something which is called a reconstruction formula. This is a field deconstruction formula, and what's nice about it, it says that if we know the field and its normal derivative on the surface of the scatterer, we can build the field everywhere. So it's the only thing we need to know. Because this is known, this is like either a Hankel function for 2D problem, or it's like from this function for 3D problem. Since here I have RRS, so probably for those who are not familiar, it will be like this. So we obtain our solution for point source located at 0, and then we just shift and we have this dependence. And so using this formula we can reconstruct field everywhere. And there is like, from this formula someone says that to solve a diffraction problem we need to build something which is called DTN map. Because usually we know one of these terms from boundary conditions. For example, if we have Neumann conditions, we know this term, and then we say we need from Neumann data to build Dirichlet data. Then it will be NTD map. This is like a very narrow sense to understand the diffraction problem. We build one boundary data from another boundary data. People say it, so you should be aware if you talk about this stuff. But I will not go into Dirichlet Neumann maps, so don't worry much about it. And so this is the first application to get the field reconstruction formula. And probably if you can get a similar expression for infinite domain, you can actually prove why your field behaves as a cylindrical wave multiplied by directivity. Because you can substitute your asymptotic behavior here, and then estimate the integral as Rs tends to infinity. And then you will get the ansatz I was showing you before. You can try to do it as home exercise, because there is like a bit of algebra. And like this, if you can represent your field like this, we usually say that you are in domain of Fraunhofer diffraction. It's like far field diffraction. Okay. What is the second application? The second application is boundary integral equation. And okay, let's consider finally. So what we do, we consider a normal scattering problem. So we have an infinite domain, we have some scatterer, we have the origin, and our domain of integration is like this. It's a big circle, which encircles our scatterer, and the second boundary is the surface of the scatterer. Let me put the difference in color is not too big. But anyway, I will denote this part as d omega s, and this part is d omega r. And similarly, let have some pointers, and U let be a solution of our diffraction problem with the incident wave. So for completeness, we need to define normal vector everywhere. This is the inverted normal vector as we defined before. And let our scattered field satisfy Neumann boundary condition on the surface. So we have a source, and also let's add a point of observation. I'm mistaken. I was moving far ahead of me. So here, for you, we also consider a problem with a point source. So like this, but this thing is just a Green's function, the free field, but this thing is a solution. So our field satisfy boundary condition on the surface of the scatter. Something that we desire. And applying, so I will use the following notation, which is more standard. G hash is it fine? Okay, let's write down Green's formula. Green's identity. So because of this delta function, we have rs instead of r, and we don't have any integration. This is like left hand side of the formula. Then we have this bit, and right hand side of the formula is like this. Again, I use double integral, but if it's a 2D problem, it's a single integral. And this term is 0 because of boundary condition. And what do we have? We don't have a boundary integral equation yet, but we again have some reconstruction formula. But this time, this reconstruction formula only needs one boundary data. And also, I forgot this bit, we have the integral on this part, but as r tends to infinity, this integral tends to 0 because of the radiation condition. So we can substitute the ansatz for radiation condition and just check that since the field decay exponentially, for example, we use limiting absorption principle, the part of integration here, so I can write it like this, but this one tends to 0 because of the radiation condition. I mean, that's something, of course, you need to check, but you know, you can either believe me or check yourself. Now you have all the tools. So we have some relation between the field on the surface and the field in the domain. But the question, what happens if we take this source and put it onto the surface of the scatterer? We can repeat all the same procedure, but we need to do it with care. And when we do it with care, we will find out that we have coefficient 1/2. And like, simple explanation is like this. To get like this part, we actually integrate over a small circle or sphere, and then we turn the sphere to 0. And as the diameter tends to 0, we actually know how the green function behaves. It behaves as some logarithm, as I was writing yesterday. But when we put it on the surface, we don't have a full sphere, we have like half of a sphere. And that's why we have this coefficient over 2. This is like the informal explanation. And this thing is a boundary integral equation. Once we put it, we have a relation between field on the surface and field on the surface. So we can discretize it and solve it numerically and get a solution of our problem. This is one approach to do it. And like the equation is called BIE, and the corresponding method usually called boundary element method. One way to solve it. Like, and as you can see, for outer scattering problems, this method is quite nice, because I don't need to solve my equation numerically everywhere. I just solve some, I can say, a complicated equation, but just on the surface. So I need much less discrete points of discretization. But like the problematic thing, actually, when you look into it, now R can be equal to RO, and that's when the thing becomes simpler. So I need somehow to regularize this integral equation before I'll be able to solve it. But people do it. That's possible. So probably a final thing for today, a final application of Green's theorem. Yeah, it's Kirchhoff approximation, which is also a very nice thing to estimate the diffractive field, and it works very well. Also, do you call him Kirchhoff or Kirchhoff?
Kirchhoff, I think.
Kirchhoff. Okay, but you've heard this name before?
Yeah.
So, but maybe you also know what is Kirchhoff approximation.
I've not seen that before though.
Yeah, okay, fine. We will learn right now. I'm not sure I written his name correctly. But he will not mind. So, what we do? We kind of try to apply field reconstruction formula, but we try to use a good guess for the field on the surface of the scatterer. And we use the idea. So we consider first a simplified situation. We have kind of a half space, just like a mirror. And then we have the incident wave coming on the half space. And we have like some reflected wave. But U on the surface is equal actually to U in if we consider a Neumann boundary condition. So it's just double of the incident field for this particular problem. It's like just a pure mirror reflection. And now I say, okay, probably that should be more or less true for obstacle of any shape. And I consider a general situation. I have usually some smooth obstacle, and I say, fine, let's field on the like radiated part. So by radiated part, so to decide which part is radiated, I need first to draw the incident wave. So I stand here. From where I stand, I can see these points. This is like radiated part. I say that here, U, the field, let it be equal to double the incident. And then I have the shadow region. I have light shadow region. Oh, this is like good guy, this is bad guy. And here it's, I say probably here field is almost zero. Of course that's not always the case, but if we consider like a high frequency case, that should be not far from the truth. And of course that should work very bad here, because here we have something which is called penumbra. And penumbra, or for like smooth obstacles, it's called Fox zone. And here actually something more complicated can happen, because here the field shifts from W into zero. Something should happen here. But anyways, I don't care about these regions. They are small, and the integration in my reconstruction formula almost happens here. So that's the only piece where it happens. And then, so here I consider the case of, again, Neumann boundary condition. And then I say a good estimate for my field is like this. If I consider pavement, of course, I integrate only over this, so what it's called prime. So the radiated bit has a boundary. And now I just have some integral, which I can evaluate. And you can try to play with this integral, and this integral will give you a very, very good approximation apart from this penumbra. Penumbra usually grows like this. So if you avoid this zone, here you will get actually a very good approximation, and everywhere outside of penumbra you will also get a very good approximation. But for, of course, like k should be much bigger than 1, but much bigger than 1, it's like, I don't know, like 3. But k, probably when I say it, I should give more formal. I should define some characteristic size and say it like this. Of my obstacle. And that's it. This is amazing. So this is, but that's actually not the last application of Green's theorem. One which is very nice. And the remaining I will ask you to obtain yourself. Of course, I'm giving you homework, but don't worry, I will not check it. You may not do it. In the ideal world, you can prove the reciprocity theorem, and it's very simple. It's just a direct consequence of Green's theorem. So you have some. This you should understand it. You have some point of observation and some source point. So you have And then what it says, so if you put source here and measured field here, it is the same as you put source here and measure the field here. It's equivalent, and you can formally prove it just using Green's theory. And the second one, as we discussed, try to prove like that's for scattered field. And the scattered field is and you can actually find the expression for this. And this thing is some integral over the surface of the scatter. So you can express the directivity of the scattered field as some integral over the surface of the scatter. So you can try it and find this expression from Green's theory. So what you do, you take the Green reconstruction formula, you substitute the far field asymptotic of the Green's function, and then you evaluate the integral, and you will have like some Fourier type integral on the surface of the scatter. And it kind of makes sense. So to obtain the far field, you just need to know the field on the surface. This is like also a common thing. So I suppose that's it. I was trying to be fast today. I hope you enjoyed. Thank you.